Hello, everybody. So we're going to do an example here that's going to kind of bring together a few of the things we've been doing in the last few videos. We will have to, we're gonna use some information to build a sinusoidal function, right? Find all those constants, and then we'll use our inverse functions and some of the trickiness around the inverse trig functions to do a little application with that model that we built. So here's our little problem. We've got a certain bay is at low tide at midnight, high tide at noon. And I'm giving you that the low tide is 10 feet and the high tide is 22 feet, right? Relative to what, we don't really know. Maybe there's a wall there and we're just marking it up there. But relative to that situation, where low is 10 feet, high is 22. Our first job is to find a function in the form given. So h of t, that would be the height of the tide. We want a sinusoidal function. We're going to use sine for it, right? We talked about in a previous video that you actually have choices. You can use sine or cosine. It just changes the phase shift that you'll have to do. So I've chosen to use sine. And then we're going to use that to find out if we were planning to be at this bay the next afternoon, when would the tide be at 15 feet? And that's where we'll get into some of the trickiness of the inverse functions. So let's start with figuring out this model, this h of t, right? So I'm going to start with a sketch of the graph using the information I have, right? So let me draw a y-axis. I don't think I'm going to draw an x-axis in this case because, well, we'll see why in just a second. So what I know, we're gonna assume that this axis, this is our h of t axis, and that this axis is at 0 hours, which I'm going to call midnight. So I'm deciding that midnight is 0 hour. The day starts at midnight at 0, goes through 24 hours, and then returns to hour 0. Or maybe we're starting today and we'll count hours from now on. So 2 days later, we'll be at hour 48 and so on. So at hour 0, at midnight, we know that this tide, let's do it in red. No, let's do it in blue since it's water. Let's pick blue. So we know at hour 0 that we're at 10 feet. And by the time we get out to hour, let's see, noon, which would be 12 hours later, we should be up to 22. So I'm going to mark off 22. I'll say that noon is out here. And then we can assume that by the time we get back to midnight, we'll be back down to 10 hours. So we should go the same distance. All right, so now my graph, let me try that again. That didn't go great. Now my graph should look something, oh, going down is so much harder. Let me just repair that a little bit. Doesn't have to be perfect, but that was bugging me. Okay, so what we're looking at is one cycle of the tides, okay? And presumably it goes on like this forever. Each night at midnight it's at low, and then by noon it's at high, and then back to low again, and this can go on and on if we scrolled this graph out. But I really just need one little picture because each day is going to be the same, so we can just start back at the beginning. I also know, and we'll figure this out in just a minute, I'm just going to draw dashed in here my midline, right? I'm just doing this eyeball sketch right now. I'm not worried about what these numbers are. I put a couple in there. And so that would be our graph. And so maybe I'll mark off a little bit along the x-axis. Isn't really there. It's down below us. I can just kind of use this space down here. This is the 0 hour. This would be halfway through at noon. And then we're back to 24. Okay, so there's our picture. So what we want to do is find this function. Okay, so let's just go through. We've got our constants. We know A, the amplitude. There's a couple different ways we think about this. We can think about it as the distance from the maximum to the midline or the distance from the minimum to the midline. Those should be the same. My picture's not perfect. But we don't know what the midline is right now, so that's not going to help us. But what we can do is use another way to think about it is it's half the distance, right? If I just go from all the way to the top to the bottom, half of this distance should be our amplitude, okay? So the way we can figure that out is 1/2, the distance from the top to the bottom is just the top minus the bottom, which gives us 1/2 of 12 or 6 feet. So our amplitude is 6 feet. We were talking about midline. That's going to be the point halfway between them. And that's another way of saying the average of these two numbers. So we add them together and multiply by 1/2 or divide by 2, and we get 16 feet. So now I know what this midline's at, is at 16 feet, and my amplitude is 6. It goes 6 feet above 16 feet up to 22, and 6 feet below down to 10. Okay, there is the first two constants. Then we'll go for B. Remember, B is related to the period, where the period is equal to 2 pi over B. But we know what the period is. This is happening on a daily cycle, so 24 hours. All right, which if we solve this for B, the equation on the right, 2/3 of this line, you can multiply by B and divide by 24, you get B equals pi over 12 hours. So the period, B is pi over 12 hours. The period is 24 hours, but that constant B is pi over, that hours should be in the denominator, hours. Okay, and I'm going to talk about units a little bit when we get all of our constants. Notice I've been keeping them the whole time. Okay, finally, we have our phase shift. The phase shift is equal to C over B. Right? We already know what B is, so that's C over pi over 12. And then this is equal to, so now I'm going to look at my graph for the phase shift. We'll notice that, again, my drawing's not perfect, but we know about the shape of sine, and we know that it goes from the bottom to the midline in a quarter cycle, and then in another quarter period, it goes from the midline to the peak, and then in another quarter period down back to the midline, and then another quarter period to the end. So if we divide this period up into 4 pieces, we see that this, oops, that's not 6 feet, that's 6 hours. This is my time along the bottom. That this first intersection point should happen at 6 hours in, right? Well, let's think of the original, the untransformed graph of sine, remember, starts out here going up, right? It would look like this. In other words, we've moved this point 6 hours to the right. So our phase shift is a +6. So let's put the units back in again. This is hours. I had hours down here. So I'm going to multiply both sides by this denominator to get C equals 6 hours times pi over 12 hours. Notice the hours will cancel, and C is just a number, pi over 2. Okay, and so now we have everything in place. H of t is equal to, and then we'll talk about the units. 6, I'm going to leave them off when I write this to keep it simple, but we'll go through and see how they all work out. B was pi over 12, t minus pi over 2, putting in C, and then plus D is 16. So let's look at what happens here with units. This is our function. This is the thing that we're looking for, and this should accurately describe the graph that we want here, right? So for instance, at 0, when t is equal to 0, that corresponds to midnight. That's sine of negative pi over 2. which is -1 times 6 is -6 plus 16 is 10. And so at 0, we end up where we want. So you can plug in a couple of values to check this, but I'm going to leave that for you. But with units, let's just notice, this is pi over 12 hours times t, our input. Well, that's hours. We're graphing this all with respect to hours. The input, the horizontal axis is hours. So when we have units of hours on t, and then we have hours in the denominator, we end up with no units, which is exactly the right units for sine, right? Radians don't really have a unit. They're a number, they're a proportion or a ratio, but they've got no unit attached to them. And C, remember, ended up with no units as well. So we've got something with no units, subtracting something with no units equals a number. Sine knows what to do with numbers. It treats them as an angle, and it spits out a number, a pure number in response. There's no units on sine. So then this whole piece here is just a number multiplied by 6 feet. And then we're adding 16 feet. So we're adding feet to feet, which is good, because if we had something not feet added to feet, we don't know how to do that. And so in the end, we're getting something that's spitting out feet. So our units work out pretty nicely. Okay, so there's our function that does what we want it to do. Let's now tackle the second part of this. We want to know when the tide will be at 15 feet. In other words, we're trying to find out when h of t equals 15. Okay, I'm going to leave the units off now. We've checked them, they work, and now I just want to be able to manipulate algebraically. In other words, we want to find the t value, so we have to solve this equation I've written for t. Okay, so let's rewrite it with the function in there. This will look like 6 sine of pi over 12 t minus pi over 12 plus 16 equals 15. Okay. So when we want to solve for t, t is inside sine right now. We can't get at it without using inverse sine. But first I want to take care of all that mess on the outside. So for instance, I want to get rid of the 16. So I've got 6 sine of pi over 12 t minus pi over 12 equals -1. So sine of pi over 12 t minus, oops, this, realize I'm writing pi over 12 for the phase shift, or for C, but that should have been pi over 2. Let me correct that. Pi over 2. So we get, I'm divided by 6 now. Sorry, I lost track of what I was doing. So I get sine of all of this is equal to -1/6. And so now we can apply inverse sine. So we take inverse sine of both sides. And I'm going to cancel it on the left, but remember our discussion when we were talking about inverses. We don't know that that's actually the case, because we don't know what t is, and we don't know if t is actually in, or this whole construction is actually in the range, the correct set of values that we're looking for. But we're going to pretend like it is for the moment, and then we'll correct at the end. So for now, I'm just going to assume pi over 12t minus pi over 2 is equal to sine inverse of 1/6. And that's some number, and we'll use a calculator to get it, but let's just finish solving for t. I can add pi over 2 to both sides. So I get pi over 12t is equal to sine inverse of 1/6 plus pi over 2, and then multiply both sides by 12 over pi to get sine inverse of 1/6 plus pi over 12. All right, the whole side gets multiplied. And this is a calculator problem. And so if you plug this in, we'll get a decimal approximation. T is approximately 5.36. Okay, so that's the time, according to our calculations, that, remember what the question was, We want to know when will the tide be at 15 feet. But remember, we were asking about in the afternoon. I'm just going to redraw this. 5.36 is 5:30 or 5:20-ish in the morning, the AM. So this is not the answer we're looking for. So let's see what happened. Let me make a quick sketch of our graph. So I'm going to draw the midline here to make it easier to draw. And then we're starting at our low point. We'll hit the midline. Then we'll hit our max, back to the midline, back to the low tide. My graph will look something like this, okay? We looked for so let's see, put in a couple of values. This is 0:10. This one is 12:22, is that right? Yeah, 12:22. And our midline is at 16. We were looking for where the height of the tide is 15. So I'm drawing in a horizontal line where the height is 15. And we found this point here with coordinates 5.36, 15. Okay, but we know that that's in the morning. And the question wants us to find the time in the afternoon. Well, we can see that right here. There's this other point. Here's noon. Right, so the horizontal axis tells us time. So I'm putting this line right where noon is. We want the time. We want to know what this coordinate is. We know its height is 15. That looks like a 16. Let's correct that. We know its height is 15, but sine inverse only gives us, remember, sine inverse gives us between, well, for an unshifted graph, it gives us something between negative pi over 2 and pi over 2. In other words, it gives us something on the other side of the y-axis up to our first maximum. We shifted everything to the right. And so it was looking for answers along this little stretch, but that's not where we wanted it. However, we can use this picture to find what we want. This distance here and this distance here are going to be the same. Okay, so we know that, so now I'm thinking about x coordinates. Right here, we're at 12. This point here is at 5.36, so this distance here is going to be 12 minus 5.36, or 6.64. So the distance there is 6.64. We want to move the same distance to the right, above 12. So we'll get 12 plus 6.64 is going to give us that coordinate of 18.64. And that's a time in the afternoon, I guess we're bleeding into the evening here, where the tide is going to be at 15 feet according to our model. Okay, so this is where we have to understand what the inverse sine does. It gave us an answer that didn't answer the question we wanted, but it still gave us the right information to get the answer we wanted. We just had to outsmart it. We had to understand what kind of a tool it is. It isn't a tool that's going to solve our problems for us, but it's going to give us some of the information we need, and we might need to do some manipulation afterwards. So again, sine inverse just looked in this, starting from this minimum up to the maximum. That wasn't where we wanted it, but the symmetry of the graph, splitting it down the middle like this, let me know that this distance here is equivalent to this, is equal to that distance there, and that let me find the value I want. Let's just finish up by looking at this at a slightly nicer graph, or let's say not slightly nicer, a lot nicer. Here's the graph of the function we were just looking at. Notice at 0 at midnight, it's at 10. At 12 at noon, it's at 22. And then back to midnight, it's back down to 10. If we zoom out, we can see it going like this day after day after day, much like the tides. I think the tides, most tides are actually more complicated, but this is a pretty basic model that is reasonable for us. Also notice here are those 2 points, 5.36. These are the 2 coordinates in this first day that we're looking at. These are the 2 times, 5.36 hours and 18.64 hours, where the tide is at 15 feet, according to the model. And in this case, we were looking for the one in the afternoon. And we used the symmetry over this line, splitting the graph down the middle, where the distance from here to here is the same as the distance from the midline to here, from here to here. Sine inverse gave us this one. We used it to find this point. Okay, that is it for this example. Thanks, everybody. I will see you next time.